Hi everyone. Today we have another type of question on chief mate stability from past papers based on GZ curves, KN curves, and dynamical stability. Let's see the question. MV Hindship is in condition number 5 at a discharge port. After discharging 400 tons cargo from number 1 twin deck, 500 from number 3 twin deck, and the entire cargo from number 5 poop deck, she has to proceed to a nearby port for balanced discharge. Calculate transfer GM and dynamical stability till 30 degrees. So we have been given the arrival condition, which is condition number 5, and 3 discharge operations took place from number 1 twin deck, number 3 twin deck, and number 5 poop deck. And we have to find the departure condition, and on the basis of departure condition, we need to calculate GM transfers and dynamical stability till 30 degrees. Okay, just to go through some theory part of KN curves. See, the shipyard provides us KN values in the form of curves and tables, and these KN values are, this is a cross curves of stability, KN curves, and they are drawn against displacement here at the bottom, and on the side we have the KN values. The curves have been drawn for various angles of yield. You can see 5, 10, 15 is written on the top of curve. So if you want to know Kn value for, so for example, 15 degrees angle of heel, which is this curve, and my displacement is 15,000. So I can go from here 15,000, go up to 15 degrees, and then go left and read the Kn value. To make things easier, they have also given us same thing but in a tabulated form. So there are tables like this. Cost curves of stability particulars. Same thing, on the left side we have displacement of the vessel, and then across we have writing arm in meters, which is Kn values for 5 degrees, 10 degrees, 15, 20, 25, 30, and then it continues to 40, 45, 60, and 75 degrees of heel. So we can calculate our Kn values from here. From Kn values, we will find the GZ value for every angle of heel. There is some explanation here. This is the transverse view, cross-section view of a vessel, and she has been healed by external forces, wind, waves, etc. So we can see WL was the original water line when ship was upright, and now the new water line is W1 L1 in inclined condition. So obviously when the ship is heeled to starboard, center of buoyancy, which was earlier on the center line just below the center of gravity G, now it has shifted out to B1, and we have now buoyancy force acting upwards through B1. This is the line of action for buoyancy force, which meets at transverse metacenter. So we draw this buoyancy force line first, and now we draw two perpendicular lines, one from the center of gravity G on this buoyancy force line, and we call that GZ, the writing lever, and another perpendicular we draw from keel K, from keel, point on the keel K, perpendicular on the buoyancy force, and call that N. So this is this Kn value which has been tabulated by the shipyard at various angles of heel, theta. Very simple explanation is here. So now I draw my ship's weight acting downward, vertically downward from center of gravity. So we can see that GZ is equal to this Pn, because both the lines are parallel. So Gz is equal to Pn. And Pn, you can see very clearly, is this complete line Kn minus Kp. So if I do Kn minus Kp, I come to Pn. And if you see this triangle KPG, which is at right angle at P, it is right angle at P, this triangle KPG, you will see that Kp upon Kg, Kp upon Kg is sine theta. So in place of Kp, from here, you see, I can write Kg sine theta. So Gz becomes Kn minus Kg sine theta. This is the formula we use to find the value of Gz, and you can see here note Kg, which we use in this formula, it must be corrected for FSE. Okay, now let's see the solution. Okay, now I need to find my new Kg. As you can see, I need the formula Kn minus Kg sine theta for Gz values. Kn values also, for that I need final displacement to extract from the tables, and Kn minus Kg sine theta, I need Kg also, I need FSE also. So initial condition number 5. So we go in the book and we go to the condition number 5. This is condition number 5, arrival condition. So initial displacement is given here 18529.3. Initial kg is 7.539, and also vertical moment has been calculated here 139700, and initial FSM is 1552. Because there are no changes in the liquids, only cargo has been discharged, no changes in the liquids has taken place, so FSM will remain same, which is here 1552. So these initial condition values I will take now in my calculations here for new kg. So initial condition number 5, as we saw, displacement was 18529.3, kg was 7.539, and vertical moment 139700. All this from the condition number 5. Now I discharge cargo from number 1 twin deck. 400 ton was discharged. I got the kg 11.17 and the vertical moment 4468. Weight multiplied by kg will give vertical moment. Then number 3 twin deck 500 tons, kg 10.37. Both these kgs are also given in the table in condition number 5. So number 1 and number 3 have been part discharged, means out of from number 1 only 400 ton was discharged, number 3 500 ton. So I get the vertical moments. And number 5 poop deck entire cargo as given in the condition number 5, 542.6, and kg was 13.76. Multiply kg with weight, you get 7466 vertical moment. And this 7466 I took directly from the condition number 5 because entire cargo was discharged. I show you again the condition number 5. So here, first we discharge number 1 twin deck, 400 tons from here, and kg was 11.17. Then number 3 twin deck, we discharge 500 tons, kg was 10.37. Then number 5 poop deck, entire cargo 542.6 tons, kg 13.76, and vertical moment was 7466. So here entire cargo was discharged, so I took even the vertical moment directly from here. In number 1 and 3 only part cargo was discharged, so I have to multiply by the kg. So now since cargo was discharged, so I will subtract 400, 500 and 542.6. All these three weights I will subtract from my initial displacement and I get 17086.7. This is the final displacement on departure. Similarly here, because cargo was discharged, so their vertical moments will be subtracted from the original vertical moment. 13970 was the original vertical moment, minus 4468, minus 5185 and minus 7466, because all these three cargoes were discharged. And I get the final vertical moment 122581. Final kg will be final moment upon final displacement at 7.174 meters. Now, as we know, FSC is given by FSM upon final displacement. So, free surface moment has not changed. As I said, there are no changes in the liquids. So, FSM I can take directly as given in the condition number 5, 1552. But the displacement has changed. So, I take now new displacement 17086.7 and 0.091 meter I get FSE. Now, as I told you, for finding the GZ values, we need to use corrected kg. Corrected kg is final kg plus FSE. So, kg is this 7.174 and this is FSE 0.091. We add, so 7.265 meter. This is the corrected kg and this will be used for calculating GZ values. Now I have to enter tables again to find transverse km for my displacement 17086.7 tons. So for transverse km we need to enter these tables here. So this is the extract from the Hindship here. So my displacement is 17086, so it is falling in between this here in 16635 and 17116. So we interpolate, this is transverse km here 8.25 and 8.27. We interpolate between these two values for our displacement. Okay, and then after interpolation I get 8.269 meter km minus kg. This is 7.174 meter. This kg I have taken. I get GM solid. This transverse GM solid 1.095 meter. Now I subtract FSC 0.091 meter and I get GM fluid, transverse GM fluid 1.004. So this was the first answer, calculate GM transverse 1.004. And now we go to dynamical stability till 30 degrees. So what is dynamical stability? Dynamical stability is the work done to incline the vessel, work done by the external forces, wind and waves. How much work is required to be done in order to incline the vessel to various angles of heel, and it keeps on changing. If the ship has to incline to suppose 20 degrees, then more work will be done. So the ship must have sufficient righting moment to bring her back to the upright condition. So that's why we have to calculate this dynamical stability, area under the curve and all. So my displacement is again here. This is two values here, 17,000 and 17,500. My displacement is 17086.7. It lies between these two figures. So for every angle of heel, it's given all. I have to now interpolate. Starting from 0, 0 will be always 0, then 5 degrees. This is 5 degrees. Then 10, 15, 20, 25. So I interpolate between these two values to get the Kn. And then 30. 30, there are two columns A and B. You need to take B as given here on the top, that the values given in column B are inclusive of superstructure. So we need the values with superstructure. So use the column B for 30 degrees onwards. Also, you can see at what angle deck edge is immersing. That's also given here, about 19 degrees. Now the question is only asking up to 30 degrees, but I have, just for sake of learning, I have drawn the full curve. So I've gone here also 40, 45, 60 and 75 also I have drawn. This is purely for learning purpose, although question is only asking up to 30 degrees. So using those tables, I first write down all the angles of heel here, 0, 5, 10, 15, 20, 25, 30, like this. And as I showed you, after interpolation of Kn values from those tables for various angles of heel, we write here. Under the angle of heel, I write the Kn value for that angle of heel. Then we subtract kg sine theta, Kn minus kg sine theta. And once again reminding that kg must be the one corrected for FSE. This is corrected kg is 7.265 meter. After adding FSE, I get corrected kg. This kg I must use here. Okay. So Kn minus and kg sine theta is, these are the values for kg sine theta. Subtract Kn minus kg sine theta and I get Gz. Now dynamical stability is, suppose they are asking at 30 degrees, then we need to find area under the Gz curve up to 30 degrees and then multiply that by displacement, and we get dynamical stability. I have drawn the full curve here. As I showed you, I have taken additional values just for the sake of learning. The full curve I have drawn here with my angle of heel here on the x-axis, and on the y-axis we have Gz in meters. So Gz, which we found here, we plot as per some good scale you can find, and plot the values for the Gz and draw the curve. And then we draw one vertical line at 57.3 degrees upward, another tangent to the curve, tangent line from 0 degree, and you get this intersection point here. Go to the Gz scale and read the initial GM. And you see that it's coming about 1 meter, and it was almost same on calculation. And I have drawn here because the question is asking dynamical stability at angle 30. This is 30-degree angle of heel. Just for explanation, I have shown this. This is the area under this curve. This part of the curve is required for dynamical stability. Although this question is not asking us to draw the curve, you may skip the drawing of the curve and directly just go with the values here. But I've done this extra because maybe there is some another question where they're asking also to draw the curve. So take this opportunity to see how the curve is drawn. Now how to calculate the dynamical stability, and then first the area under the curve. As you can see that from 0 degree, always remember we must take 0 also, which is upright condition. From 0 to 30, we have 1, 2, 3, 4, 5, 6, 7 ordinates. So I can use Simpson's rule number 1. So ordinates are my Gz values. These are my Gz values, and common interval between the ordinates is 5 degrees. But you will see that the degrees cannot be used in calculation, it must be converted to radian. Okay, these are the GZ values here after Kn minus Kg sin theta. And I decide to rule number 1, Simpson rule number 1. Multipliers will be 1, 4, 2, 4, 2, 4, 1. You write under the GZ values. Now multiply GZ value with the Simpson's multipliers to get the area function, and then add all the area functions with sum of the product. For area function I get 6.476. Okay, now the formula, as you know, for rule number 1, Simpson's rule number 1, formula is h by 3 into sum of the product for the area. Now h, which is 5 degrees, the common interval between ordinates is 5 degrees, I have converted to radian by dividing with 57.3, because 57.3 degree is 1 radian. So I convert to radian. 5 divided by 57.3. This becomes my h. So h will be 5 upon 57.3. Then we have divide by 3 also. Multiply by sum of the products for area. 6.476. Area under the curve up to 30 degree, I get 0.188 meter radian. Dynamical stability up to 30 degree will be this area under the curve multiplied with the displacement W. So 17086.7 into 0.188, 3212.30 ton meter radian. So this is the second answer, dynamical stability up to 30 degrees. Okay. I hope that I've been able to explain in detail all the steps here. Well, you can go through again the video, and if there are any comments, if it helped you or you have any questions, you can put in the comments and I'll be happy to answer. All right, thank you very much.